Welcome back. We'll have the third lecture of today, day 2, which will be given by Professor Nimesh Kumar Sahu, is titled Overview of Controllers for DC-DC Converters Used in Green Hydrogen Energy Systems. So,
Today I will be discussing about, that's why I wrote the title Overview of Controllers. As you saw in the previous slides, we have a lot of converter topologies, and we use them for different applications, and their performances are also different. So, similarly, how to control these DC-DC converters, that we are covering here. But basically what I will do, I will take you through a bunch of controllers that you can utilize. Some of them are already utilized and tested with the electrolyzer. Some of them are tested with other applications which can be aimed to be used for electrolyzers, and some of them can be further researched. Okay. So, that is why my content will be mostly so before jumping into the controller, all these first 3 points I will just give you a brief, because all you have covered this, just to link with my rest of the things to the previous, and then I will spend more time on key requirements for the controller, types of controller, and some of the case studies which are available on the literature. Okay. So, again I will just brief you like why we require hydrogen. As we know, hydrogen is now considered as an energy carrier, and it has wide range of applications. You have been seeing this from the morning, and mostly it can be used in industry, power sectors, home appliances, and also it can generate heat or electricity, and that electricity you fed to the maybe some of the electricity production or generation through the use of fuel cell concept. Okay. So, now another one of the important aspect, also hydrogen used for some kind of synthetic gas or liquid fuels, we call sometimes that sync fuels, and there is a statistics shown on the graph is basically the prediction of electrolyzer capacity in gigawatt range over till 2050. Okay. So, the statistics is given in two aspects. So, if you consider the global warming at 2.8 degree centigrade scenario and global warming at a 1.8 degree centigrade scenario. Okay. So, if you they have considered both types of global warming condition, and they have projected that by 2050, if you consider global warming 1.8 degree centigrade, so the electrolyzer capacity is going to be close to 4500 gigawatt by 2050. Okay. And in India also we have a mission called National Hydrogen Mission. If you can go through that website on MNRE, so you will find that we have also a target to achieve some amount of production of hydrogen by 2030. Along with also we have the target to achieve 500 gigawatt of non-fossil fuel based power generation in India by 2030. So, as renewables are also coming up more and more in India and globally, so we also expect this hydrogen will be a game changer, because it will definitely complement what are the issues we face with the renewable intermittency, whether it be solar, whether it be wind. So, basically it will act as a you can say the flexible load. So, most of the people you might have heard about passive loads, mostly power electronics group of people, they test everything with a bunch of passive load, whether R load, RL load or capacitive load, or some kind of electronic load also they use. But again this electrolyzer is basically we consider it as a responsive load or flexible load. Okay. And as you have seen before, the load nature is not linear, where you cannot simply apply your Ohm's law to estimate the current by passing through a voltage. So, basically there are different types of dynamics in terms of over potentials available in the hydrogen electrolyzer load. So, that makes the load nature being a non-linear, or you can say the piecewise linear. Okay. So, you have seen the VI characteristics already for the electrolyzer load. So, depending upon that, how this power electronic interface, whether you connect to DC grid or whether you connect to AC grid, how you have to merge these power electronic converters. I am not saying power electronics will be totally changed, but whatever the existing, let us say you are using some kind of topology for electric vehicle. So, whether that load nature and electrolyzer load nature be same, and what requirements for the electrolyzer load from the control perspective a converter should give, because as we know a proper nature of the electrolyzer load is a low voltage and high current device. So, you cannot simply connect to the grid scale DC link voltage and generate electricity. So, what you need to do, you definitely step down the voltage. What we see, we have different topology between your AC connection and DC input to the electrolyzer. Again, it is not only low voltage, high current, there is also efficiency also concerned, the stress on the power electronics is also concerned. So, looking at those aspects, we are going to design the controller. So, this is also a way of hydrogen production methodology. It is actually the you can say the review of all the slides Professor Jahangir showed. We have a different way of producing electrolyzer, but if I if I want to show the main target is this PV or wind or this kind of electrolysis. So, basically we are focusing on green hydrogen, because we are using some kind of green energy, whether it is solar or wind, to produce electricity. Okay. And those are mostly efficient and what I say environment friendly, and that is why they all over globally people are promoting this kind of green hydrogen technology. And also if you see the share of hydrogen use by 2050 to the right side of the slide, by 2050 you see the sink fuels. If you see the yellow color distribution, the sink fuel where hydrogen is used as a fuel for the vehicles, that use is expected to be more and more as we go towards 2050. You can see the bar chart to the right, and the yellow color, if you see the length of the yellow color is increasing. That means the share of sink fuel in the total hydrogen electrolyzer load is hydrogen electrolyzer application is growing day by day, and the top shaded portion also there, which is basically the grid injection. What we are talking about, the hydrogen at grid scale, at the megawatt level, where you connect the hydrogen and help the grid utility operator to some kind of provide ancillary services, which will definitely be discussed by Professor Hossain in the future lecture. So, this is what we are, and there are other applications you see, industry, transport and buildings, and also refining industry. So, this is also a prediction till 2050. Now, where the role of power electronics comes, okay? Because as I told, this green hydrogen production requires some kind of power electronic interfaces, because grid is current grid is AC. Also we are slowly going to a DC grid, but still we have AC loads and AC currents. So, if you are connecting or planning for a grid scale electrolyzer, so if you see the top level, it is a, if I consider a medium voltage AC grid, basically our transmission level Indian grid, you can say. If you want to connect a electrolyzer to a Indian grid, which is mostly the transmission line voltage level, so you will have some kind of transformer, which is basically we use a low frequency transformer. Then you have a rectification, because you require the generated AC to first convert to DC, but the power rating is in the megawatt level. So, whatever and voltage in megavolt, so or you can say so then the generated DC also we can expect in the range of kilovolt or tens of kilovolt. Okay. And that DC voltage you can simply cannot give to the electrolyzer stack, because electrolyzer requires low voltage. So, that is how you, if you see the middle line, then you convert that DC output of the rectifier, then the input to the DC-DC converter, and that DC-DC converter, whatever the configuration we discussed in the previous lecture. And once we have this DC-DC converter conversion, we make sure that we achieve several things. First, we achieve a high voltage conversion ratio, because as I told, input is high voltage, output will be low voltage. Okay. So, in that range we require a high voltage conversion ratio, and because you see there are so many power electronic interfaces are involved. So, definitely there will be different kind of losses involved in each stage of power conversion, whether it is a AC-DC or DC-DC. So, as losses are involved, so whatever the power you get it from the grid, so you may not expect that much to reach to the electrolyzer. Let us say I am connecting a 500 megawatt electrolyzer, but I cannot expect the same power I achieve at the electrolyzer input, because I have some power electronics interfaces. So, those are switches, conduction losses are there, there are other losses also involved. Okay. So, what we can do? So, we can design some kind of converter and its respective controller to make sure we achieve the optimum efficiency, and that is how achieve the optimum power input to the electrolyzer. Then that can be helpful for our hydrogen production. Okay. So, that is one way of, if you want to connect directly your electrolyzer at the grid level. So, in that case this electrolyzer will be at scale. When I say it is not a single electrolyzer, it is a stack of, or you can say bunch of electrolyzer that can generate power in the level of megawatt. Okay. Apart from that, you can also have kind of distributed local generation using wind power, and that can also you can use it for hydrogen production, and that can be a microgrid structure, you can say, like wind energy again it generates AC. Okay. So, that AC has to be converted. Actually, that converter can be a back-to-back converter, but is basically at the end you need to have a AC to DC rectifier, and then you go for this electrolyzer stack input. Similarly, this, so particularly wind driven electrolysis and solar driven electrolysis, we have two specific lectures coming up in the next days. Okay. So, there we will discuss how this operation happens and control happens. The last one is also you can have some integrated battery energy storage system, and one thing I want to say you, this if I compare a battery energy storage and hydrogen energy storage, and if I compare that PQ curve, what I say basically when you say 4 quadrant 2 quadrant operation, PQ curve, if I see, you know, all of you know battery acts as a bidirectional device. So, it can source active power, it can sink active power, it can source reactive power, it can sink reactive power. Okay. But for a electrolyzer, it is a only sink for active power, it cannot source. So, basically to source the active power you require a kind of fuel cell, and that is another way of injecting using hydrogen and injecting power back. But having said that, there are some modern technology comes that have single equipment you can use as a fuel cell as well as hydrogen electrolyzer. We basically call it as a reversible electrolyzers. So, that you can use it for both fuel cell and electrolyzer by changing some connections. But when you say reversible, the materials, electrodes are, you know, they are developed in such a way that just only electrical input output connection, like the same machine I can run as a generator, the same machine I can run as a motor. That depends on what input I am giving and what output I am getting. Okay. Similar way, new technology for let us say solid oxide electrolyzer SOEC, they have reversible SOEC available in the market or globally also. They can use it for both operation, whether you want for both only hydrogen production or you want to get it back. So, that is the basic PQ I say characteristic difference between a battery and a electrolyzer. So, electrolyzer is only sink for active power, but it can source and sink for reactive power. That makes it operate in, if I take the P axis, P in the x axis, Q in the x axis, y axis. So, if I try to draw the operating zones of electrolyzer, it comes in first and fourth quadrant, correct. So, Q positive, Q negative, and P is second and third quadrant, P is negative only, but for a battery all quadrant you can operate. Okay. So, that is the big difference between the characteristics of the electrolyzer and a battery. Yeah, this is only one slide. I will not go to these things because already discussed. So, again I will say isolation is important. Where we do the isolation? Because if I see the previous slide, I can use a low frequency transformer here to have some kind of isolation, but again when I design this transformer in the MVA rate, you can imagine the cost of the transformer. So, what people can do, instead of using this high frequency transformer, a compact structure, you can involve the isolation in the DC-DC converter. Okay. So, this transformer will be a high frequency transformer and it will be low compact in size. So, and also cost will be you can manage, because hydrogen itself is heavily cost. Now, several discussions are going on. Okay, hydrogen is giving so much power, so much facility, ancillary services, but what about the cost? What is the techno-economic analysis people have done for the hydrogen? Is it compatible with battery? If okay, battery is a short storage, hydrogen electrolyzer is a long storage device, but this techno-economic along with this ancillary services has to be compared. Otherwise, this megawatt scale hydrogen electrolyzer investment cost itself very high. So, you have a balance of plant structure apart from this normal electrodes and all. Also, you will have power electronics for that. Also, you will have the big location. If I say 500 megawatt of electrolyzer, it will be like this kind of room, you can imagine. So, that you are going to put on the field. So, definitely high investment cost is there, but with that investment cost, what are the services, what are the benefits you are getting? So, that comes under something kind of techno-economic analysis. So, that has to be yet done. So, that is why. So, one of the thing you can mitigate, power electronics people through power electronics group researchers, what they tell, you can use some kind of solid state transformers. So, which is basically high frequency, low cost and compact in size, and you can get rid of that grid side transformer which is very big. Okay. Because you require isolation for the electrolyzer. And why you require isolation? Because grid is very vibrant. So, anything, anytime, anything can happen, and by that time this electrolyzer should not be impacted. So, that is one of the key requirement for the design of controller for this DC-DC converter. How to get robust output when the input voltage goes through random changes, because that is expected, you cannot avoid that, that is connected to the grid. But having the input side disturbance, how can you get rid of the outside, get rid of the disturbance at the output voltage or current, or minimize the disturbance. So, that is one of the, because the disturbance again affect the performance of the hydrogen production. If it reduce the efficiency, might sometimes degrade your membrane or electrode. So, all these things, chemical erosion, everything might happen, or might it will totally trip the load. So, all these things are kind of what I say, precautions you have to think of when you design this types of controller. Yeah, so based on that isolation, basically what I told you. So, that based on isolation, you can have isolated or non-isolated. Again, isolated you have this many 4 types. I have taken some of them, not there are other, because power electronics people every day they are coming up with a new topology. So, they are keep on doing research and development, but these are some of the proven technology has been used for different application. They are now trying to use it for hydrogen electrolyzers, and some of them are working, some of them are needs to be updated, some kind of switches they need to update, some kind of controllers they need to update. So, all these kind of things they need to update it. Okay. So, you can this is a very good paper in the reference, you can go through all the converter details, topology details, it is given. Okay. Whoever interested in developing power electronics for hydrogen electrolyzer. Yeah, so what I was telling, these are the key parameters for a converter. One is number of switches. So, there are, as I told, power electronics people, for them it is just only building the topology. So, they come up with these many switches because you use interleaved so many parallel branches, but whatever number of switches, because the more number of switches, more number of switching loss, and the output again your efficiency will be getting down, because electrolyzer might not require the 100% power requirement every time. So, it can vary 20 to 30%. The DC-DC converter, the moment it runs at a lower rating, it will definitely give you lower efficiency. So, keeping all that in mind, how much number of switches you are using, can you optimize it? So, if you can optimize it, you can definitely use them. Second is number of inductors, because you know the simple single stage buck converter, there is a single inductor involved. But if you go on increasing, making it more modulated interleaved structure, or you make it like isolated DAB structure. So, the different inductors also, input side, output side inductors comes into picture. So, design of that inductor and all this comes into picture. Second is current ripple coefficient, because the ripple factor that actually directly related to the efficiency of the electrolyzer application. So, if you see a normal single stage buck converter, you will see some kind of ripples in the output current, okay, because then there are different topologies coming. Okay, one stage is giving ripple, then I will have 3 more stages, I will cancel out the ripple at the output and give the normal current to the electrolyzer. There are structures are there interleaved, they use, you know, one inductor generate ripple, output inductor, other inductor is there in parallel just to neutralize the ripple, so that at the converter output all the current you add them, then the total ripple get cancelled and you get the input current ripple free. So, that much technology also there. If you see the previous paper, you will get some idea like that interleaved structure, why it is more preferred. Okay. So, sometimes power electronics people come, they can achieve even zero current ripple, okay. But there are some talks I have come across, or some industry I have come across, even zero current ripple also not good for hydrogen electrolyzer, because you need some kind of ripple to generate that electrolysis process. So, if you give zero current, that may not be reached to that, you know, activation potential what you have studied. So, that kind of, you know, threshold you have to maintain. So, all these things comes into picture. Then voltage stress again, because this once you operate it as longer time, because a long storage device, longer time, and these two switches will definitely comes under voltage stress. Okay. Then duty cycle, some of the converters are available, so they can operate up to certain duty cycle. So, how to make one converter to achieve a wide range of duty cycles you can operate, so that it will give you the required output. And finally, the application based, whether you are using at the simply a microgrid level, you are using at a transmission or grid at scale level. So, depending upon high power application, low power application, you use different kind of topology. Yeah, so these are again the key requirement for the controllers. One is stability, because once you talk about the grid scale, so everything requires some kind of stability. Okay. And stability I am not selling it is only to DC-DC converter, is a system level stability. Whether it is a, first of all, stability comes from the grid, what kind of grid you have, it is a strong grid, it is a weak grid. So, there are different parameters you measure the strength of the grid. Then along with that grid, when you operate this kind of power electronic interfaces, the AC-DC converter with their controller. So, I am not sure how many of you have gone through this control system stability analysis, small signal stability analysis using Bode plot or some kind of Nyquist criteria. So, when you do that, that theory even still applicable in power electronics and power system, but again you have to design the total system matrix. Okay. And if you see and evaluate the system matrix, in that matrix you will, each element will have the power circuit parameter as well as control circuit parameter. First thing is power circuit, people do not bother to change, you cannot change them, because controller you have the flexibility to change, is basically a firmware. It is not that much cost compared to the power circuit when you put up a converter and transformer, all these things. So, controller you can change, but that controller again has to be designed how your system matrix behave with a small signal disturbance. Okay. So, that is one kind of stability analysis you should take into picture. Having the stability, then fast dynamic response. Now, what we studied in the previous section, PEM electrolyzer compared to alkaline is very fast acting. Within few second or sub-second, what professor mentioned, it respond to the external disturbance. Let us say grid acts, there is some frequency disturbance happens at the grid side. So, being a responsive or flexible load, your job is to respond to that frequency change. So, okay, so your electrolyzer based on your operating performance, you are fast acting, grid also fast acting, but in between if the interfaces are not fast acting, then you cannot, your response cannot reach to the grid, right. So, in between this DC-DC converter and their controller should provide that much faster dynamics, so that whatever the nature of fast dynamic nature of the electrolyzer load can quickly respond to the frequency disturbances or voltage disturbances. Okay. So, that is why we require fast dynamic response, wide operating range. When I say again it relates to the previous one, wide duty cycle, you can operate through a wide duty cycle range. Then accuracy and regulation, because accuracy, when you design controller, two things comes into picture. One is the robustness and how much accurate it is. Robustness, you can measure it like dynamic response, faster settling time. Again, along with that, you should have accurately tracking whatever the reference is given to you. So, when you design these two design the controller, these two factor you take into picture, accuracy and robustness. Because some controller gains you give you faster response, but steady state they are less accurate, there is steady state error is there. Some controller give you very fine accurate response, but they take a longer time. So, your controller gains you design as a trade off between these two. You do not want very fast, you do not want very slow also, and you do not want less accurate also, you do not want more close to 100% accurate. Okay. So, apart from that, there are other things are there, you require minimum ripple, improved efficiency, reliability, safety and adaptability. Okay. Yeah, so type of control, as I told, I will give you overview, but again you can check the literature, I will share with this. So, based on, as I told, one way we can use the control system basics, how you design a controller. So, those basically comes under analytical controller. So, one of the popular controller, proportional or proportional integral or proportional integral derivative. So, this kind of controller you can use some kind of average system averaging method, use the system state space vector, state space matrix or kind of Bode plot. You can use them and analyze the stability zone, and to remain in the stable zone, how much you design the controller gains. For instance, for Bode plot, it is the phase margin, gain margin, how much is the thumb rule, is you have to maintain that phase margin. For that phase margin, what is the controller gain you are coming up. Of course, there is not a single controller gains is available universally. People do here and there, but there is also a mathematical validation why you choose these range. So, this mathematical validation is your basic control system theory. So, that comes under analytical control. Apart from that, PID, you have linear quadratic regulators control, SMCs, backstepping, model predictive control, and there are some adaptive control. Apart from that, intelligent control. Okay. Let us say I am giving you an example, PI controller. Let us say I design it based on my state space averaging method, I get some Kp and Ki, proportional gain, integral gain. I use the system, run the model, that is running in provide me robustness, accuracy in steady state operation. But what is the guarantee that will give the same response when I have a dynamic disturbance or very high large signal disturbance. So, for that reason, what people do, they design this Kp, Ki by using some kind of heuristically tuned, some kind of training and testing model they use by the use of AI/ML technique. They try to tune the Kp, Ki based on the events or based on the events those controllers pass through. They train the system in such a way that if certain kind of events happen, that Kp, Ki will be updated real time. So, you need not be fixed Kp, Ki what you derived from the analytical calculation. If it is a steady state, they will be matching with the analytical. If it is a large signal, it will update automatically, so that you need not to be go to the unstable region. Okay. There are other techniques are like fuzzy logic controllers are there, reinforcement learning based controllers there, and neural network controllers are also there. So, I am not telling these are new, but for hydrogen electrolyzer all them has to be yet tested in a full scale. Okay. They have been tested in their own domain. Let us say control system people or people are working on IIML, they do not bother about the load nature, they do not bother about the source nature. They just give some kind of very ideal disturbance and prove they are okay, this is tracking or not. But when you have constraint like in the very big system, you have so much nonlinearity involved in the load, in the source, the other things are there. So, in that whether this controller need to be updated, that is yet to be tested, and this is open scope for you also. This is one way of classifying the controller. The other way is basically the operating or operating performance wise. Okay. One is linear control and non-linear control. So, hydrogen electrolyzer is a linear or non-linear load. So, okay. So, because of that, nowadays these non-linear controllers are getting more noticed. Okay. Because linear controller, as I told, it is mostly designed assuming that this system will only see a very minimal disturbance. Okay. But in reality, this electrolyzer load nature is very non-linear. As you see the VI characteristic curve, some region is very if I say electrolyzer, it will start from some what we say some starting over potential, which is independent of current, and then once the current starts, it will follow some kind of non-linear structure. It is not a straight line like ohmic or a resistive load. Okay. So, to accommodate which operating point you are using, so you cannot design simply a linear controller, because you have to cross through a non-linear trajectory, non-linear path. Any operating point on the VI characteristic, the electrolyzer can operate. So, for that we have, along with this linear controllers, we have non-linear controllers. So, here you can have also this SMCs, backstepping controls, sliding mode controller, then PID also there. But linear again proportional PI controller all comes in linear type of controller. Okay. Then last type of division is model based, model free. Okay. So, when you design the controller for let us say for example, we are discussing a DC-DC converter control. So, depending upon the topology, the dynamic equations of the model will change, right. So, there are some students here, I hope you have finished your power electronics and control system course, right. Okay. So, when you if you have tried any time writing the dynamic equation, let us say for a buck converter I want to write the output voltage and current equation, I have to write some kind of differential equation, right. So, that again changes with respect to what kind of topology you are using. It is not always same. If you are using a single state buck, you are using a interleaved, you have a DAB. So, depending upon which control input you want to change. Let us say I want to control my input current, someone wants to control the output current, output voltage, input voltage. So, depending upon which parameter you want to control, or someone wants to output power control. So, depending upon which parameter you want to control, accordingly you have to frame a dynamic equation, and based on that dynamic equation you have to design the controller, because basically you will have a if I go to a very basic control design from the control system basic book, you will basically all these converters and all we call it as a plant, right. So, basically you design a controller for a plant. So, takes the feedback from the plant output, then it pass through a, if I am considering feedback control, so plant output can be voltage, current, power, whatever, then you pass through a controller, and then with some, because all are switching devices, some kind of PWM signal or some kind of pulse modulation schemes you pass through the control output that generate your switching pulses for the switches. So, that is the fundamental. So, now this feedback what you take, the plant model you have to write down the equations, differential equations. then what are the control output comes from the controller output, that again has to go. So, that switching model, some madam was asking whether we can, yes, we can. Many people in what I say nowadays, because system is no more simple, now you have to model the grid, you have to model the rectifier, you have to model the DC-DC converter, then you have to run the simulations in the whole model. So, if I can show you sometime the complete model of a grid connected electrolyzer, it will be very huge, and the time taken for simulation in the MATLAB model, it will be very high, unless until you have a workstation or some kind of high computing devices. Okay. So, what is the people are doing? So, what you can do, let us say you are not talking about any kind of new topology and you are more concerned with controller. So, the power electronic interfaces you can convert switching model to average model. Okay. All the switches you need not to operate and operate at their own sampling frequency. You can convert the switching model to average model, and while you convert the average model, you get rid of this pulse width modulation schemes, and that makes your system faster. So, for testing your controller, average model can work well. Okay. Or another point, if you are bothered about only DC-DC converter, that converter you can do in average model and you can test with other being the switching model. So, that is how you can optimize the time of simulation. So, when I say average model, there where you come with the mathematical model of the converter, where I am telling you to write down the dynamic equations for output current voltage. So, once your control input comes, how it is used in the mathematical model of the particular topology. If you can write down that mathematical equation, and again that equation gives you output voltage and current, same thing you can give to the feedback controller. Okay. So, that is the whole purpose. Then I will start giving very brief 4-5 controllers. So, you can go others from the literature. So, as I tell, proportional control, it has mostly two parts, proportional part and the integral part. I am not showing the derivative part here, proportional, integral, derivative also you can use. So, proportional control, what you can do? So, it is used for several applications. I am not telling for electrolyzer, starting from control system people to machine people to power electronics, power system, even mechanical people sometimes use also proportional integral controller, because it is very easy and highly adopted in the industry. Okay. Because industry, some of industry people are here, so they always like simple solution but effective solution. So, there are other highly sophisticated nonlinear controllers are there, but those are only existing in the literature so far, because those are only R&D scale proved. So, you may not get those controllers in the industry products. Okay. So, this is, as I told, this E of t basically whatever, it can be error signal. If you have a reference current to track, if you have a reference voltage to track, if you have a reference output power to track. So, all this error with the measured value you can consider as a error signal. That error signal has to be multiplied with the proportional constant, and there is a integral gain. Okay. So, output of this is U of t. So, U of t I consider as a control input. Okay. That you can use for your mathematical model. So, this is, you say, is very easy to implement, but there are issues. When I say what are the issues? Issues have been observed in case of electrolyzer. It might be working proper for your inverter, might be working proper for your machines and drives, but issues have been observed in electrolyzers. I will show some simulations. So, because electrolyzer have so many constraints to fill. So, if controller does not fulfill those constraints, so there is no need of using this kind of controller. Okay. So, if I take a simple, you can say it is an interleaved converter, right? Two parallel inductors you are seeing, and we have 4 switches, and the electrolyzer load is basically a electrical equivalent of a PEM electrolyzer. Okay. So, as I told, this total converter I will consider as a plant. So, plant is giving me 2 output, V naught and I naught, which I want to control. Okay. That V naught and I naught I am measuring at the output of this converter, and I am using a dual PI controller. So, I am dual means I am using PI controller for controlling both voltage and controlling for current. So, basically we design the voltage little bit. So, if I say time is less, but when you design the controller, you some bandwidth concept also comes. So, bandwidth is related to your response time. If you have a high bandwidth, response time is fast. If a low bandwidth, response time is less. So, basically we design the voltage control bit of low bandwidth, so that we can accommodate the current control very fast. Okay, current has to be controlled very fast. So, I am here using the inner current control and outer voltage control, and if you can see, for both controlling both of them, I am using the PI. PI represents the Kp plus Ki of integration of that, whatever I showed in the previous slide. And if somebody want to design this controller, so he can represent this model. Okay. So, this model, if you see, the orange color part, okay, is basically the plant transfer function. Not only plant, it has the PWM gain, and there are some what I say other gains are also observed, like basically here you have the DS disturbance, then this is your plant model that generates the output current. That current pass through a feedback gain, which we call HI of S. Then after that, GVI is the voltage to current ratio, V0 by I0 S, that you will get after framing the dynamic equation of output voltage and output current. Generally, when you write the differential equation, then do the Laplace transform, then get the output by input, right. So, that V0 by I0, you do that, you will get the GVI of S, that transfer function you can get, and that basically depends on your system parameter, how much output capacitor, inductor, whatever is there. Then from that you take another, you have another feedback gain, which is HV of S. So, now you have two control loops, you can see, right. One is current control loop, one is total outer voltage control loop. So, you have to design first in such a way that bandwidth of these two control loop don't clash. Okay. So, the thumb rule is basically you design the voltage control loop a bit slower and current control loop also bit faster. Okay. So, here you can use some kind of, I am not I do not have time to show the transfer function, but I can share with you some paper. So, you can derive this equation, actually that is derived from the output of this converter topology. So, how you derive this equation, then you frame the open loop transfer function, open loop transfer function. Okay. Then once you have the open loop transfer function, you apply the Bode plot, and in Bode plot you get basically magnitude response, phase response, and from magnitude phase response you get the phase crossover frequency, gain crossover frequency, and for each frequency you have some phase margin and gain margin. So, finally, you will be given some phase margin and gain margin. Using this, you design those two controllers. So, you have to do reverse way. You fix your phase margin, you fix your gain margin, then you come back and end where you will get the value of this Kp Ki for both output and input loop. Okay, clear? So, that is the whole story of PI controller. So, what is the observation? If you see some of the results I have taken from some paper. So, if the first signal is basically the input DC, if you see the topology here, I used basically a DC constant battery type, but in reality it is not constant, it is basically a DC link of your active front end rectifier, AC to DC, which is connected to the grid. So, that can anyway give some DC fluctuation, right. But for ideal region, I am taking a step change in the input, and due to the step change you can see you have a huge overshoot in the output voltage, which is not recommended, because this voltage goes as an input to the electrolyzer. You cannot have this much high overshoot, and also due to this disturbance you see there is a change in if you see the second graph is basically how the secondary current, basically in the topology secondary current, how it looks like. So, basically what I mean to say here, so input disturbances for a PI control directly affect the output performance. Okay. But we do not want this kind of high overshoot. It might be seeing 9.5 volt here in this paper, but you can imagine for this overshoot current also will go this much ampere, it is written something 31.5, but if you remember the yesterday simulation, if I consider a megawatt level scale, the current can reach up to kiloampere. Okay. So, this if I measure or scale it up the current, the last curve current into kiloampere level, you can imagine how much overshoot in the current you are getting, and that much overshoot might affect your electrolyzer. Okay. So, how to avoid that? There are different types of nonlinear controller. First is something called sliding mode controller. So, what it does is basically switches between different structure and drive the system state trajectory onto a predefined sliding surface and maintain it there. Okay. So, this is it is actually updated every time based on how the system is behaving. Okay. Now, here the first thing is in sliding mode, from the name we have to design some kind of or decide some kind of sliding surface. So, if your operating point is lies very far away, so the controller job is to bring that operating point towards the sliding surface and keep it operating there itself. So, that is the job of the basic fundamental of the sliding surface. So, choosing a proper sliding surface is very much important, and based on that sliding surface, so before I go further, so this is the basically very what I say fundamental steps to be adopted for doing a sliding mode control. As I told, first is dynamic model validation, because it is basically a model based control. So, you have to accurately model the topology, that let us say DC-DC converter. Based on its mathematical model, you have to derive the control. Second step is sliding surface selection, because sliding surface based on the sliding surface you will have several types of SMCs, which I will show next. Then after you select the sliding surface, you have to define a control law, which we call it quick reaching law. So, what it will do? It will give you a fast converging time. So, if your operating point goes very divergent way, so if your quick reaching law is proper, so it will ensure that your reference and measured value track very fast wherever it operates. Okay. Then finally you have to make sure that whatever the sliding surface you decide, with that your controller you can use some kind of Lyapunov stability analysis. So, many have you gone through nonlinear control system, right? So, when you go in your you go to the nonlinear control theory, there where you cannot use the state space analysis and all. So, basically there you have to use some kind of mathematical function, iterative function, where you use to make sure that or there are some kind of graphical analysis also there, that will ensure you to prove the stability for a nonlinear system. Okay. So, this is the basic step of the sliding mode control, but depending upon, let us say, what sliding surface you are using, that will give you 7 to 8 types of sliding mode controller. What quick reaching law you are using, that will also deviate from each other. So, based on 2, 3 it can have different thing, but when you start designing SMC, this is the way. Okay. This is what I was telling, the sliding surface. So, let us say your operating point, these are the upper bound, lower bound. If your operating point somewhere operates outside this region, so it will take to this point and it will try to operate the system within this range. Okay. So, you have to design this sliding surface. Okay. So, how you design, that depends on which kind of sliding mode control you are taking. Okay. And here you can see the control input is basically your equivalent control, basically UQ of t minus k signum S of t. So, S of t is basically the sliding surface you select. Okay. Again I will share, you can go through this paper reference given below to know more the mathematical things. Okay. So, as I told, Lyapunov is a very known stability theory to perform the stability analysis for nonlinear systems. Apart from that, you have Hamiltonian systems and some kind of phase plane analysis. So, many things are there, but again as you interested, you can go through that, but those theories are being taken and utilized here to analyze the stability of the system when you use nonlinear control theory. Okay. So, basically you have to define a positive definite function at your operating point, and you have to, there are different conditions like first derivative is less than equal to 0, then your system is stable in the sense of Lyapunov. But how to choose that V of x is actually important. Okay. Then if it is only less than 0, they call it asymptotically stable, or if it is greater than 0, it is called unstable system. Okay. This is the basic Lyapunov theory, but you can utilize. So, where the changes will come, how you define that V x function. Okay. Once you can formulate that V x function from your control theory, then you can follow this thumb rules. If your first derivative is coming in which range, then you can say system stability zone. This is also another Lyapunov same thing. So, I will skip for time being. Yeah, as I told, these types of SMCs. So, this only differ what is the nature of S of t, sliding surface. Okay, you can have conventional, integral, global, continuous, terminal, dynamic. So, it only varies how you choose your S of t or sliding surfaces. Again, the references I have given, each controller is given there. Okay. I will show some of the controllers. As a conventional already I showed you. Let us say I tell about integral sliding mode control. Okay. Again, I am taking, if you see my sliding surface, I am taking S of t is basically a Ka times of error plus Kb times of 0 to t error dt. Okay. Using that sliding surface, my final control law is this. For Pi controller, my u of t is Kp plus Ki by S. Okay. Now, for the this ISMC, integral sliding mode control. So, you can see this S of t is used here, and you have some other gains. So, you are also taking, because let us say I am controlling the output voltage, my V reference I am taking the reference voltage first derivative, and this is some kind of disturbance term if you want to add to your controller. Okay. So, this is your final control law which you will use to control your buck converter, DC-DC buck converter. And here if you see these gains K, Kb, alpha, beta all has to be properly tuned. So, for tuning purpose, as I told, you can use some kind of nonlinear control stability theory, let us say Lyapunov or whatever. And if you can tune those parameters properly, it will ensure you can have a wide operating range for your electrolyzer. It is no more directly affected with input disturbances. So, I will show you a this is another way, another type of sliding mode, terminal sliding mode. If you see again, my sliding surface equation change here. Once I change my sliding surface equation, then I will formulate my u of t equation with the control input. So, this changes depending upon different types of controller. I will give you the slides. You can design this for a particular buck converter. You can take simple single stage buck converter and you can compare these equations. It is very simple equations. You just measure the error signal, give the derivative signum function, and then this delta. So, particularly this tuning parameter you have to be carefully judge and give, then you can compare which type of sliding mode is best suited for your application. Okay. So, this is one example I have taken, as professor I have told. This is a full bridge DAB converter, dual active bridge converter. So, you can see there are 8 switches, and here the switch 1 and 4 diagonal switches operate at the same time, and there are different modulation schemes actually there for this DAB converter. That modulation schemes depends how you shift the switching pulses between the input bridge to output bridge. Let us say input bridge you do not give any phase shift, but output bridge you give a phase shift of phi. That scheme is called single phase modulation scheme, SPS. Okay. Let us say input I give a phase difference or phase initial phase, then output I shifted with a phase with respect to the phase of the first bridge. That is something called dual phase shift scheme, DPS, or sometimes people call extended phase shift. Okay. So, those are modulation scheme, like for inverter you know SPWM, sinusoidal pulse mode with modulation, space vector modulation. For DAB there are SPS, DPS and TPS, triple phase shift control, but those are like most complex. So, single phase shift is very simple and straightforward, And for this converter, if you see, the power transfer equation is basically this, and this phase, this is the phase you have to control. So that control power is shifted from primary bridge to secondary bridge. How you control this? There are, you can use any kind of controller. The final output will be phi, like u of t I was writing, right. From u of t you have to convert to phi, because it is a phase. That phase has to come here, and by controlling this phi you control the power transfer. You can have a, let us say, if I consider my AC side grid is connected this side and my electrolyzer is connected this side, then you can have a isolation transformer. So any disturbance, this is preferred to make sure that it is least affected by input disturbances, which is our main objective, correct. And here also the design parameter for output L and C, if you want to have. So basically this N is basically the transformation, you have a transformer, right. So transformation ratio, here you can have a high voltage to low voltage transformer, right. If you have a 6 kilovolt input, and but I want 262 volt at the electrolyzer input, that is your N equal to 6000 by 262. That can be your N, and this is your switching frequency of the each switch, okay. And this is the power, and there are some capacitor, you know, you design based on how much output voltage ripple you want to have. There are some standard 5%, 10%, and apart from that, how much peak current, how much output current. So it will give you the value of output capacitance, okay. So this is I am telling for designing the C, and if you have any L here. But apart from that, in between, you know, its equivalent circuit also contains R, C, L circuits, right. Those are will be dependent on electrolyzer performance. This is basically the DAV converter designing parameter, okay. So I will finish in 5 minutes. So integral sliding mode, I already told this, so you can see some response. So I give a step change, you see in the current or voltage there is no overshoot, right. If I compare to PI controller, I have a input side, I have a dip change, but here I see some steady state error, but that is manageable for electrolyzer. It will be within the operating range, but the important factor is there is a smooth change in the current for a big jump in input. I am showing you a ISMC control output connected with a electrolyzer. So that tutorial I will show you in the tomorrow. Today me and my student will show you the electrical and electrochemical model development of electrolyzer in MATLAB Simulink, okay. Then tomorrow that electrolyzer will connect to a DAV converter and run this simulation and show you, okay. And maybe if time permits, that DC side I will connect to a grid forming inverter. Then it makes a total system from grid side to the electrolyzer side, okay. I will try the last one, but DAV with these things I will show you in the MATLAB Simulink, okay. Okay, so this is another way is model predictive control also. Here also you have to predict the different parameters. Let us say I will not go in detail much. This is a interleaved converter. So how the control philosophy happens. So basically you have a output voltage tracking you want to do. So you take your reference voltage and output voltage you measure and you pass through a PI control. This is normal PI controller, okay. So that gives you a current references, okay. Now this current reference, using current reference and some system parameter, this ILA, ILB, ILC is passed through each parallel branch. Using those current and some switching strategy, you predict the next sample of inductor current and output voltage, okay. So there is some kind of prediction required, and that prediction model you can use, various methods are there. That's why there are different types of MPC controllers also there. And then after that you can have some kind of cost function, because here why you require cost function, because you have parallel layers of power converters, buck converters, right. So if you don't properly coordinate among them, so your control objective of getting output voltage less ripple you will not get. So there should be a proper coordination between these parallel connected converters, okay. For that you need to have a cost function. So each sample, that K if you see is a discretized model many of you might know discrete domain modeling, right. In continuous we use Laplace, in discrete we use Z, signal system if you have covered so far. So, that is the discrete model, that k, k plus 1, k minus 1 is like the consecutive samples. So, in next sample you have to predict based on the present sample and previous sample. That is what you have to do for a prediction model. Also cost function also you have to see that in each sample current in one of the parallel branch is more than the other two currents. Then similarly, if it kth sample, first sample you get the first L1 branch getting the more current, K2 you develop, sorry not K2, K plus 1 sample you will say that my L2 branch current is more than the other two. So, that is how you coordinately operate. Otherwise, if you operate them independently, if I do not have that cost function, if I remove that kind of cost function block also, I can operate. But in that case, individually parallel converters, they will operate and make sure their output voltage is ripple free, but you will not get the net output voltage ripple free, because you do not have coordinated operation. For only coordinated operation, you are having that cost function, so that they will, each branch will coordinate with each other, switching will happen accordingly. If switching happens accordingly, so they will produce coordinately the output voltage which will be ripple free. Okay. Again, details of this work you can read this paper given below. These are some mathematics behind that. Cost function of phase shift, as I told, in my first sample my first inductor current is greater than the other two. In my second sample my second inductor current is greater. In my third sample my third inductor current is greater. Fourth sample again my first inductor current is greater than the other two. So, this is the cost function block you are seeing that is implemented. Okay. That is how you coordinate between three branches. If you have multiple branches, you might have multiple mode of operation. Okay. As we are telling, the left side is without cost function, the right side is with cost function. So, this paper claim that with cost function they achieve less output voltage ripple. Okay. The others also operate, but they measure the ripple content. They told if the coordinated operation happens with the help of a cost function, they can achieve optimum operation. So, basically this type of control is called finite control set model predictive control, FCS MPC. Okay. So, you can see fuzzy theory is normal, but there is an application in electrolyzer. Again they are doing output voltage tracking. So, this shaded part is your fuzzy logic control. You have a fuzzifier and defuzzifier, and you add your like knowledge, what you say if else condition. If input is this, output is that. So, that inference you have to, inference engine you have to feed the information, like what are the conditions you want to feed it. Then the input parameter it will fuzzify, it will pass through this information, true false, then it defuzzify and generate the duty cycle. Okay. Okay. So, the control details and all you can find in this paper. So, here they only tested with a variable R load, but if you are interested you can replace this R load in different models of electrolyzer and check this control response. That will be a good work. Okay. Because the same response you might not get when you have a nonlinear load with a electrolyzer principle. Okay. So, these details you can see from this paper, and results there is a comparison. If you see the voltage tracking, output voltage tracking between a backstepping and a PI controller, the red color is reference, your reference is started from here, stepped up, then step down and again step down. If you see this overshoot which I was talking about, PI controller, that can get rid of a smooth tracking by IBC, integral backstepping control. Okay. So, that is one of the advantage of this kind of nonlinear control over the linear type control, and for electrolyzer particularly we want nonlinear controller to have a wide range of operation. Okay. So, yeah, so this is my conclusion. So, controller is the backbone for a power electronic converter, because switches are there, the way you treat them they will give you the performance. So, controller, how you design, what is the requirement for electrolyzer? It is a high voltage step down, high efficiency, then low current ripple, wide range of duty cycle. All these things are your constraint or objective to design a controller. So, based on that you will design, and some of the controller gives you the good response at the cost of a high computational complexity, because PI you see there is 2-3 mathematical operator. But if I see tomorrow we will see a very sophisticated SMC controller, there will be so many mathematical operator, trigonometric operator, inverse trigonometric operator, signum operator. We can imagine how much computational burden it will give to a DSP board. That is what your firmware, right, for a power electronics converter. So, that much computational complexity you have to sacrifice to get a good response. So, again research are going on how to optimize with this simplicity, easy to implement, again robust response. Okay. Yeah, so there are so many scopes are available. If some of you are interested, some people might be interested in the converter topology, some people might be interested for the control theory, some people might be interested from the system design perspective. Okay. So, with this I am concluding my talk and happy to answer your queries if any. Thank you.